Today's video features a geometry problem from the Harvard-MIT Math Tournament. We have a regular hexagon ABCDEF. P is a point in the interior of ABCD such that the area of triangle PAD is 23 and the area of triangle PBC is 20. We have to find the area of the hexagon. Okay, we can take advantage of the symmetry of the hexagon about the line AD. So we can focus on finding the area of ABCD, which is a trapezoid, and then we can just double that area to find the area of the hexagon. To begin, let's call the side of the hexagon X. Let's also drop segments from points B and C perpendicular to AD at points M and N. Now, we have rectangle BMNC. So MN is also X. Notice that we also have two congruent right triangles, BMA and CND. Also, you can easily check that each interior angle of a regular hexagon measures 120 degrees. So angle FAB measures 120 degrees. By symmetry, AD bisects angle FAB, and so angle MAB measures 60 degrees. It also follows that angle MBA is 30 degrees because BMA is a right triangle. AB is also X. In right triangle AMB, AM is opposite the 30-degree angle, so it is half the hypotenuse AB. So AM is X over 2. Since triangle BMA is congruent to triangle CND, ND is also X over 2. Now, in right triangle BMA, MB is opposite the 60-degree angle, so it can be represented by square root of 3 over 2 times X. Now, notice that AD is just the sum of X over 2, X, and X over 2. So AD is just 2X. Now we can come up with an expression for the area of trapezoid ABCD. Using the formula for the area of the trapezoid, we have area of ABCD is equal to 1/2 times quantity BC plus AD times BM. Substituting x square root of 3 over 2x and 2x, we have 1/2 times quantity x plus 2x times square root of 3 over 2 times x. Simplifying, we obtain 3 square root of 3 over 4 times x squared. So now we just need to find the value of x squared in order to find the area of trapezoid ABCD. Now how can we do this? We can use the two given triangles. Now, let's draw a perpendicular segment to both BC and AD, passing through point P. Notice that the altitudes of the triangles are contained in this segment. Now let's represent the altitude of triangle PAD by h sub 1 and the altitude of triangle PBC by h sub 2. So now we can represent the area of triangle PAD by 1/2 times 2x times h sub 1. We know that the area of triangle PAD is 23. Substituting this value, we have 23 equals 1/2 times 2x times h sub 1. Solving for x times h sub 1, we have x times h sub 1 equals 23. Similarly, the area of triangle PBC can be written as 1/2 times x times h sub 2. And we know that the area of triangle PBC is 20. So we have 20 equals 1/2 times x times h sub 2. Solving for x times h sub 2, we get x times h sub 2 equals 40. Now let's add these two equations. So we get this equation. Notice that in the resulting equation, we can factor out x in the left-hand side. So we get x times quantity h sub 1 plus h sub 2 equals 63. Now, recall that we have already solved the distance between BC, and AD. And that is just square root of 3 over 2 times x. And observe that it is equal to h sub 1 plus h sub 2. So we can replace h sub 1 plus h sub 2 in the equation by square root of 3 over 2 times x. So we have the equation x times square root of 3 over 2 times x equals 63. Simplifying, we get x squared equals 126 over square root of 3. Now we can solve for the area of trapezoid ABCD. Substituting this value in the equation, we obtain the area of trapezoid ABCD is equal to 3 square root of 3 over 4 times 126 over square root of 3. Simplifying further, we have the area of ABCD is equal to 189 divided by 2. So now we can solve for the area of the hexagon. The area of the hexagon ABCDEF is just twice the area of ABCD. So the area is 2 times 189 over 2. And so the area of the hexagon is 189 square units. And this is our final answer.